Good evening to everybody. Welcome to this lecture on overview of remote sensing and remote sensing platforms and sensors with specific reference to disaster management applications. Now, if we talk about remote sensing, it is the method, that is the art, science, or technology of observing an object or a scene or a phenomena using instrument-based techniques. Now, it is called remote because the observation is done from a distance without actual physical contact with the feature of interest. And sensing means that you are detecting here energy such as light or any other form of electromagnetic energy. So taking measurements from a distance without actually being in physical contact with the object is the process of remote sensing, and it enables us to observe and study natural phenomena and other objects in ways that would not be possible by human capacity. And it also enables us to take measurements or observe a phenomena or an object across great distances using wavelengths of light which are invisible to human eyes. In short, let us just quickly go through the history of remote sensing. It began with the invention of the camera when the first photograph was taken. And at that time, the platforms that were used were hot air balloons, kites, pigeons, because the aircrafts had yet not been invented. And with the invention of the aircrafts, airplanes, especially during the World Wars, this technique developed as a military application, and later on it developed into civilian applications with the IIRS satellite launched in 1972, which we today know as the Landsat series of satellites. So the Earth observation systems for civilian applications began with Landsat. That was the first satellite for civilian applications, Earth observation system. We now do remote sensing with sensors and platforms which are used to create image data of the Earth. So a sensor would be a device like a camera which would record electromagnetic energy, and platforms would be those carrier beds which are used to carry a sensor, that is a satellite. Now, in short, the process of remote sensing, basically the physical process requires an energy source. If it is passive remote sensing, that is, we are using or dependent on an external source of energy, then the most commonly used source of energy is the sun. And the sun's electromagnetic radiations travel through the atmosphere. While doing so, they interact with the constituents of the atmosphere, whatever they come in contact with, that is gaseous particles, water vapor molecules, pollen grains, smoke, fog, dust, any other particle that they may come in contact with. Now, when they do so, there could be absorption or scattering, and only that amount of radiation which continues to travel in the direction of the feature of interest, in this case the surface of the Earth, is of use for remote sensing. Now, once it reaches the feature of interest or the target, then there are other interactions like transmission, absorption, and reflection or backscattering. So that amount of energy which is reflected towards the sensor, and in passive remote sensing, it interacts with the constituents of the atmosphere for a second time while traveling back to the sensor, and then the energy which reaches, or the signal which reaches the sensor after all this attenuation or loss, it is recorded at the sensor in the form of a digital image. The digital image is an array of numbers which which comprise the digital image. Then, if the sensor happens to be in purview of a ground receiving station, data is sent to the ground receiving station and downloaded there. Otherwise, it is recorded on board, and we have sensors for various applications and also for communication. So there are Earth observation sensors and sensors for communication and weather prediction. Now, before we begin remote sensing, we should, as users, be familiar with the properties of the electromagnetic spectrum. So the spectrum of electromagnetic energy ranges from the shorter wavelengths to longer wavelengths. And there are several regions of the electromagnetic spectrum which are useful for remote sensing. The most used region, although a very small region, is the visible portion. This is the portion of the spectrum where human beings are also able to see. We are not able to see any other region of the spectrum, that is the infrared, microwave, or the shorter wavelengths of ultraviolet or X-rays. Although we use them for remote sensing, but as humans, our eyes are only sensitive to the visible portion, that is from 0.4 micrometers to 0.7 micrometers. So from violet to red, these are the wavelengths of the visible spectrum. So as I mentioned earlier, the two major atmospheric effects are scattering and absorption, and scattering occurs when particles or large gas molecules present in the atmosphere interact with and cause the electromagnetic radiation to be redirected from its original path. The result being that some amount of radiation does not continue to travel towards the feature of interest, and therefore that amount of energy is lost for further remote sensing process. Similarly, in absorption, this causes the molecules in the atmosphere to absorb energy at various wavelengths, like ozone and carbon dioxide, also water vapor molecules. So they absorb radiation, and again, this amount of energy is now not available for the remote sensing process. The interactions with the target are of importance because this is a manifestation of how the targets behave or are seen or manifested on the image in terms of their reflectance or backscattering in different wavelengths. So a graph or a plot of the wavelength versus the amount of reflectance in percentage is called a spectral signature curve or a spectral reflectance curve. This can be made for different land cover features, and then we are able to analyze how these features interact or behave when different kinds of electromagnetic radiations interact with them. So for example, if it is clear water, then in the visible and infrared regions, there is very little reflectance in the visible region, and in the infrared, all or almost all of the energy is absorbed. So in the infrared region, it will appear as a dark feature on the image because most of the energy is absorbed. On the other hand, if it is green vegetation, healthy green vegetation, then it reflects most, about 50%, in the infrared region, right from the red to the infrared. Then there is a plateau. These are water absorption bands. So vegetation features in the infrared wavelengths will reflect more and will appear as bright features. So the physical condition of the object is of great importance, and we assess the amount of reflectance versus the wavelength to interpret what the feature might be at the time the image was taken. Now, as I said, again, the digital image is an array or grid of numbers. Each cell is called a pixel or a picture element, and the amount of energy is depicted by the digital number associated with this cell or pixel. Then we also need to know about the resolutions or the specifications which define the kind of image or data set that we will be working with. So resolution means the ability of the sensor or the system to give information at the smallest discretely separable quantity in terms of distance, if it is spatial resolution, the narrowness and the number of wavelength bands, spectral resolution, time period at which it is sensed, temporal, and the radiation or the energy differences that it can measure is the radiometric resolution. So the four kinds of resolutions for remote sensing data are spatial, spectral, radiometric, and temporal resolutions. So spectral resolution basically means which regions of the spectrum and how narrow those bands are. Is it a narrow bandwidth or is it a broad bandwidth? And how many number of bands does the sensor have? Whether it is panchromatic or multispectral or hyperspectral. So similarly reflecting objects, if there are similarly reflecting objects like different species of trees or different minerals, etc., then a better or finer spectral resolution is something that we would look for. Now, we can also have true color composites wherein the blue band or the blue channel or the blue wavelength is seen through the blue color gun of the display device. The blue through the blue, the red through the red, and the green through the green. So we get a true color display on screen. Then because we may have in the image a higher number of bands than 3, because the display system has only 3 color guns, red, green, and blue. So we may need to choose a different color for a display. So then it becomes a false color composite, as is the case here. We have infrared through red, red through green, and green through blue. So there all vegetation features appear in the color red, and the built-up areas and sand is in cyan tone, and all other features, blue, dark blue is water, and so on. Bright white features are dry sand or dry riverbeds or fallow fields. Then spatial resolution means the physical dimension of the area that the sensor sees at one time. Right? It also refers to the amount of detail that you can see. So spatial resolutions of 1 kilometer versus spatial resolution of 1 meter. The 1 meter spatial resolution will give you more details, and you will be able to see, say, individual buildings, roads, etc. And on a 1 kilometer spatial resolution or pixel size, the larger area will be visible but less detail. So if you see this is the AWIFS sensor at 56 meters, the same area at 30 meters, approximately same 23 meters, IRS list 3. IRS is the satellite system and list 3 is the sensor. Then Aster at 15 meters. So now if you appreciate, this is 30, this is 60, and this is 15. So now some features have started to become clearer. This is a panchromatic image with single band, no color, black and white at approximately 6 meter pixel size. At same area at 4 meters pixel size. Now you see many features have become clear. Buildings, road, a road lined with trees, agriculture fields, orchards, and many other features. Same area at 1 meters pixel size, but panchromatic, black and white image. Then radiometric resolution means that how sensitive is the sensor to slight differences in energy. Is it able to discriminate very slight or small differences in energy, or is it not? So the finer radiometric resolution, the more sensitive it is to detecting small differences in reflected or emitted energy. So this also defines the quantization rate or the quantization level or the number of grayscales that the user will be able to see or the sensor is capable of discriminating. So a 1-bit image will have 2 colors, 0 and 1, and so on. A 7-bit image will have 128 number of gray levels. That is, pixel values will range, or DN values will range from 0 to 127. Or if it is 8-bit quantized image, then 256, and values will range from 0 to 255 and so on. Right? This is just to show you if you have a higher radiometric or a finer radiometric resolution, then objects become clearly visible, the boundaries become clearer, and details may also be seen under occluded areas. Temporal resolution, as the name suggests, is about how frequently does the satellite revisit the area of interest and acquires a new image. So this depends on the instrument's field of view and the satellite's orbit. So we can have a repeativity of different time periods depending upon the sensor system. Now, if we talk about platforms, then platforms could be ground-based. We could mount cameras on ground-based systems, could be airborne systems or aerial sensors mounted on aircrafts or UAVs. And if they are mounted on satellites, then they are spaceborne systems. We can have geostationary satellite systems and sun-synchronous satellite systems. Usually, the geostationary satellite systems are for weather and communication applications, and the sun-synchronous satellites are Earth observation satellites, which operate at an altitude of about 700 to 800 kilometers, and they have a fixed time at which they cross the equator, approximately 10:30 a.m. local time, and the satellite orbital plane is near polar, and therefore the altitude is such that the satellite passes each place at the same local sun time. This is how the animation shows you. This is how it operates. So the satellite orbit north-south and the rotation of the Earth from west to east work together or in tandem to allow a complete coverage of the Earth's surface after it has completed one complete cycle of orbits. Now, these are some land imaging satellites: Landsat, Spot, IRS, which is the Indian system, NOAA, Iconos, RadarSat, this is a microwave satellite, ERS, also a microwave satellite, NBSat, JERS from Japan, and ELOS, also from Japan. Then sensors, which could be active or passive, and the types of sensing systems could be optical, which operate in the visible and near infrared, thermal, and microwave sensors. So each one has its own advantage or limitation and is used for different applications. Specifically for disaster-related applications, the thermal and microwave systems have special significance along with the optical systems, of course, because there are certain disasters or events which would be observed only through, say, microwave data, as is the case for floods or forest fires, which could be seen in the infrared wavelength or the thermal wavelengths, volcanic eruptions, and so on. So here also we have imaging sensors and non-imaging sensors, which could be in turn active and passive, depending upon how the sensor operates. Now, microwave sensing is important because it is able to penetrate, because of its long wavelength, it is able to penetrate clouds, smoke, fog, etc. So especially useful for areas where, we have a prolonged monsoon periods, that is the tropical regions of the earth. So whenever we have a cyclone or a flood or long periods of cloud cover, microwave data comes in very useful, because optical data during those periods does not give us much information. Then the sensors could be a cross track, how they scan. They are scanning line by line. They could be a long track, where they used linearly aligned arrays, which consist of numerous charge coupled devices, or CCDs, which are positioned end to end. So each scan line has a number of CCDs, and the forward motion of the satellite scans each successive scan line. Then we also have high resolution imaging modes, which give us fine spatial resolution. So time delay integration and step and stare are two methods which we can use. Again, in case of disaster management applications, if we require very high details in terms of the pixel size, then these kind of sensors can be used. Now, some of the sensors on board the satellites are the multispectral scanner and the TM and the ETM Plus on Landsat, linear imaging self-scanning system, that is the LIS sensors, the panchromatic pan sensors, etc., are on the IIRS series of satellites, the WIFs and AWIFs 2. Then we have OLI, again on Landsat 8 and 9, and AVHRR on the NOAA satellites. Now we come to the portion where we shall talk about why use Earth observation systems, particularly for disaster management applications. So Earth observation has been widely applied to disaster risk management, including preparing for the event, response, recovery, and also for mitigation applications. This technology provides extremely useful information for researchers, decision makers, and planners, and it consists of different types of sensors, as we have seen in the introductory section. We have microwave, we have laser sensors, that is the LIDAR, optical sensors. We can have in the types of images, we can have multispectral images or hyperspectral images, and even panchromatic images, which are single band images. Multispectral images are images which have which use tens of bands, and hyperspectral images have very narrow bands. In their number ranges from to a few hundreds. Then we could have different kinds of platforms depending upon what kind of data is required, from unmanned aerial vehicles to aircrafts to spaceborne platforms, and also ground-based systems could be operated. This enables the monitoring and modeling of geohazards over regions at different scales, because it would give us different fields of view, and we could have different spatial resolutions. So different scales in which the ground observations may not be possible due to different constraints like physical or political or inaccessibility of the terrain. Now, Earth observation can also provide high spatial, temporal, and spectral resolution. So we can get data at different kinds of spatial resolution. So we can see the same area in different details, levels of details. Temporal variation, that is at different time periods. So specifically for disaster related applications, a pre-event data and a post-event data can be compared to see how much damage has happened, where it has happened, which areas need priority attention, where can the which roads are intact or which network of transportation is intact, so that can be used to reach the affected area as quickly as possible, and aid can reach the affected area, and so on. Spectral resolution helps us to be able to see through ranges of the electromagnetic spectrum, which otherwise we would not be able to see as human beings, because we are able to see only through the visible spectrum. Then stereo imaging or stereo mapping is also possible. That is, we are also able to visualize the area in 3 dimensions by using specifically acquired data sets which are called stereo pairs, and these enable us to do mapping or information extraction in 3 dimensions. Also, these sensors, some of them are all-weather, have all-weather imaging capabilities, and the time of day is also not a restriction for the passive sensors. Then improved satellite and sensor technologies, increased frequency of satellite measurements, and easier access and interpretation of the Earth observation data have all contributed to the increased demand for Earth observation data for different kinds of applications, specifically disaster management related ones. So Earth observations, when combined with complementary terrestrial observations and with physical models, have been widely used to monitor hazards, and these have revolutionized our understanding of how the Earth system works. Now, a number of natural disasters may be effectively studied with EO data, like earthquakes and related structural hazards, ground displacements, landslides, fires, flooding, and tsunamis. We can also look at man-made disasters, like maybe a nuclear disaster or maybe a fire in an urban area, and so on. So if the ground ruptures or if there are seismic hazards, then all these will be visible where the buildings have fallen or where the bridges or roads have been affected, etc., can be seen easily on the satellite data. Also, soil liquefaction, there are several studies where you can analyze using the images and other ancillary data. The liquefied regions can be interpreted on the image and analyzed. Then if there are ground displacements, that is, if there are faults, etc., or there has been a displacement during an earthquake, then these damaged areas can be identified and proper planning can be done. Landslides can be studied because the Earth observation data gives you large expanses. You are able to see the large expanse, and you're also able to see, along with the other ancillary data, that which areas might be vulnerable, which are going to be affected, and so on and so forth. So unstable regions, etc., which may fail or which have failed, and what are the regions that they will affect, can all be studied and predicted. Then fires, forest fires or urban fires, or these can all be studied using different Earth observation data sets. So we can use thermal data for this kind of application because there it is temperature characteristics, where how the heating and cooling of the feature of interest happens is studied using the thermal region of the spectrum. So fires due to various reasons, it could be due to flooding, or it could be forest fires, it could be fires due to coal mining, etc., in certain regions where coal mining happens. Those areas can be studied and mapped, and which areas would be affected in times to come, which have already been affected, and what is the condition of those areas, where do we require priority attention, and so on and so forth, can all be done using either EO data or aerial data. Sometimes it needs to be corroborated with ground observations and some field work. Similarly, flooding, flood hazard zonation and flood prediction can be done easily using stereo data together with optical images. So with the help of the stereo data, three-dimensional views or data sets, which are called digital elevation models, can be generated for the terrain over which the flood is expected. and then we can do a simulation study by analyzing that with some amount of rise in water, what will the area, which areas will be affected? So how many buildings, what will be the loss of life, which buildings could be damaged, if it is a multi-storied building, how many floors will be affected with each meter of rise in water, and so on and so forth. So very high resolution elevation modeling is also possible with the help of stereo data, that is images which have overlap, and then using a technique called photogrammetry, a digital elevation model can be generated. This can also be used for simulating fire scenarios to see how much the spread of fire will be in hilly terrains, and so on and so forth. So flooding from the river or the reservoir, how much area would it flood, which buildings would be damaged, if it is a multi-story building or if it is a single-story building, how much area will be affected, which floors will be affected, and so on, where there can be, people can save themselves. If it is a high-rise building or say a 3 to 4 story building, can they use it, to save themselves from the flood, or other damage to life and property can also be assessed using this data set. Then, if there happens to be a tsunami, then depending upon the depth of the water, how high the waves are going to travel, and then what areas would they drown, or which structures along the sea coast, up to what level is the damage going to happen. So tsunamis are usually they usually happen after an earthquake, so an underground earthquake, and so those kind of applications for interpretation of the data are possible. Then the other kind of hazards that we can study or with Earth observation data or satellite data are forest fires, as I said, dust storms, snowstorms, or avalanches. These can be mapped and studied, and also the area extent to which the effect of these hazards will happen. So how large an area will it affect, and how many people or what kind of property, the loss of life and property will happen, can also be studied using these for these kind of hazards. Then microwave data will be specifically useful for cyclones, hurricanes, flood related disaster studies or management applications, because in optical data and also infrared data, the cloud covered areas, there is not much data because the wavelengths or electromagnetic radiations in these wavelengths are not capable of penetrating the clouds, and therefore we only get an image of the cloud and not the area underneath the cloud. So microwave data usually is the only source of data with which we can use these, which we can use for times when there are floods, cyclones, hurricanes, etc. Now, microwave interpretation requires certain special characteristics to be studied, that is a separate subject in itself, and maybe later on in your module, in the course, you will be able to do a better understanding of the microwave images. Then volcanic eruptions. So thermal data would be of great importance here, because the crater, heats up the lava, which is of very high temperature. The thermal data would give us clues which optical and other kinds of data would not provide. So we could use multiple data sets together to study one disaster event. This would give us different kinds of information which we can club together as clues and do better interpretation. Similarly, man-made disasters like, say, spills, oil spills, chemical spills, etc., or any other hazardous material that spills, explosions, which could be due to nuclear explosions or chemical explosions, etc., sometimes train accidents or plane crashes, etc., or maybe groundwater contamination. This happens to be a matter of concern and is a continued process that needs to be studied, and people get affected, but they do not know why they are affected. It is because of contaminated water. Uh, if there has been an accident, like a train accident or a plane crash, so identifying where the parts of the uh, crashed airplane may have fallen, or to rescue people and so on and so forth. So EO data would give us very crucial information. Uh, Oil spills, again, microwave data comes in very useful when we need to look at oil spills, and the extent of the spill needs to be identified. Similarly, other like chemical explosions due to a chemical in a chemical factory or in a nuclear factory. So these kind of applications are possible for both natural disasters and also for man-made disasters. Earth observation data can be used for a wide variety of in a wide range, and interpretation of the data can be done to identify damaged areas and also priority areas where the aid needs to be sent. So as we said, these techniques can be classified into different types according to the sensors. They can be optical, multispectral, thermal, or hyperspectral. Could be active sensors or passive sensors. They can be on the platform basis. They can be satellite-based, aircraft-based, unmanned aerial vehicles, or ground-based. And we require multi-temporal data for change analysis. LIDAR data or stereo data can be used for generating a digital surface model or a digital elevation model from which 3D information, surface elevation can be extracted. Now, for change detection, a pre-event and a post-event correlation can be done. So there are some in situ observations which are required, and with this we can, the remote sensing data which is observed from a distance, if we have some ground truth information from ground observations, then we are able to do a very exact prediction of certain events and disasters that may happen. So several decades of work on disaster relief has shown that Earth observation can provide valuable information using a combination of several kinds of data sets like optical and microwave technologies together, or maybe thermal and optical data sets together, or stereo data sets and microwave data together, or LIDAR data sets, or multiple kinds of data sets can be used together. So Earth observing technologies utilize information from spaceborne, airborne systems, and through a variety of active and passive sensors. Now here we try to give you an overview of how these applications are actually put to use. So people have mapped spatial distribution of collapsed buildings, right? Then optical remote sensing specifically has a long history, and it has continually improved both spatial and spectral resolution. So the technical advantages and familiarity, that is, we are very familiar to seeing things in this region of the spectrum. So this is the most commonly used region of the spectrum, and this makes them irreplaceable for Earth observation systems. So it also contributes to damage assessment, etc. But the presence of shadows and variations in solar illumination and geometric distortions sometimes restrict the use. However, visual inspection is a very widely used method to produce realistic inventory of damage. And several people also use digital classification as a means of rapid detection of damage. So when you use pre and post event data sets, edge extraction can give you the building boundaries of the buildings which are intact. This is the pre event image and this is the post event image. So when you do edge extraction, then intact buildings will come as closed edges. Similarly, change detection. So pre-event, post-event, and the changes are highlighted. Similarly, microwave sensors are useful in situations where clouds or darkness impede the work of optical sensors. We have SAR sensors, radiometers, scatterometers, and radar altimeters. Now, sensors such as SAR, INSAR, and are other attractive tools for disaster management because here data sets can be obtained without being affected by weather conditions, which is a characteristic of microwave sensors. So deformation rate can be mapped. Now we come to hyperspectral mode sensing, where similarly reflecting features, so types of vegetation can be mapped, types of minerals can be mapped, different kinds of man-made material can also be distinguished. So even if they have, the features have a characteristic of reflecting similarly, because we have hundreds of bands and those bands are very, very narrow, so we will be able to make a distinction between different materials using the hyperspectral data sets. Now, quickly we shall go through a few images taken from different platforms, UAVs, aerial platforms, and Earth observation platforms. So this was the pre-event image of the Kathmandu earthquake in 2015. Now here you see all the buildings which are intact. After the earthquake, several of them have been damaged. So this tower, you see, all of that has been damaged. This is a ground photograph. Only the base of the tower has remained. Whereas in the pre-event image, we can see the features as intact features. Then on a mountainous slope, all the buildings have been damaged. Kathmandu earthquake again. So you see here, these areas are all damaged areas. These are ground images of those same areas. This is a pre-event and post-event comparison again. Similarly here, this is microwave data. So ALOS pulsar data, which is a Japanese sensor, gives you before and after scenarios after an earthquake. Now interferograms have been made to generate 3D information. Then this is the tsunami. Pre-event, normal ocean conditions, and when the tsunami strikes, so very high waves. Now this is pre-event in an area in Indonesia. This is post-event. So entire area has been devastated by the waves of the tsunami of 2004. Now this is the nuclear power plant in Japan, Fukushima. And here you see this is the pre-event image. This is the industrial area, that is the power plant, nuclear power plant. After the tsunami struck, the earthquake happened, etc. So you see quite a lot of damage can be observed. Buildings have been broken down, towers have collapsed, and damaged areas can be seen. Similarly, again, pre-event and post-event images prior to the earthquake and after the earthquake. This is again Banda Aceh in Indonesia, damage after the tsunami of 2004, December 26, 2004. Quite a lot of damage can be seen. This is Sri Lanka again before and after the tsunami. So here you see this is the pre-event image and this is the post-event image. The entire beach, etc. has been washed away, and near the coast all buildings, etc. have been damaged. So again, pre-event and post-event. So you see here and here. Similarly here, all this has been washed away due to the landslide and floods. Now here there has been a fire in the refinery. So this is the refinery before the event, pre-event, and this is the refinery post-fire, the post-event image. Now we can compare the two, do a change detection study and analyze which areas have been damaged and where priority attention needs to be given. Again, pre and post-event images to analyze how much damage has happened where. So this is Kathmandu as viewed with the Pleiades satellite after the 2015 earthquake. These are the tents, etc. for the giving refuge to the affected people. And these are the ground photographs depicting the areas where the damage has happened. A few more examples of before and after scenarios. This is the before, entire annihilation. Even here, the airport has been washed away and flooded. All the buildings, tree cover has been washed away. So with this, we come to the end of the lecture session. We will take a break of 5 minutes and then take up queries if you happen to have any.